lecture, we'll be talking about two very important concepts. One is curse of dimensionality and principal component analysis, one of the linear dimensionality reduction techniques. So let's understand the concept of curse of dimensionality through an example, okay? So let's imagine that we are plotting the height of the students of this class in a Cartesian plane, and the data is actually scaled through a min-max scalar, okay? In another video, we have explained what is data scaling or feature scaling. So the min-max scalar actually compresses your data in the range. If your minimum is 0 and max is 1, then within this 0 and 1 range, okay? So we are plotting their heights, okay? So we first split this x-axis value into 3 point bins, and we plot the highest person from the class, okay? So because this is a scale value, so the highest person will possibly sit here, okay? And let's plot the rest of the students from this class. And this is a likely configuration. We don't expect that the shortest person of the class is half the size of the tallest person, okay? So this is a reasonable assumption. We can have some extreme cases, but this is a reasonable assumption, okay? Can we hypothesize that the entire class will fit in this area? If the shortest person is just around 60% of the height of the tallest person, so what will happen if we have data points within this region, all the data points, then we will cover 40% of the between 0 and 1 in the x-axis values, okay? So we can safely say that our data is actually covering 40% of this space, okay? So what happens that if we do the same for another feature, let's say weight, it's more likely that the data points will sit here, you know? So 40% of the height, and then maybe 40% of the weight. And the data points are more likely to be sparse, you know? So it's very likely that the coverage will reduce from 40% to, let's say, 10 to 15%, okay? So let's assume that we actually are covering 10% of the two-dimensional space here, okay? So we can quickly see that the coverage actually dropped from 40% to 10% when we increased our number of features from 1 to 2, okay, right? The other way we can tell that the empty space actually grown from 60% to 90%. So if I subtract 40 from 100, then that will be 60, and this will be 90 if we subtract 10 from 100, okay? So the empty space grows from 60 to 90% when we increased from one-dimensional data to two-dimensional. So the empty space actually grew from 60% to 90% while we are plotting the height and weight of the students in this class, squeezed in a range from 0 and 1 for both axes, okay? So imagine that if we add 2 more dimensions, okay? So now the data has 2 dimensions, but if we add 2 more feature dimensions, then this empty space will go from 90 to maybe even 99% or even more, okay? So what's happening? With the increase of number of features, it's very difficult to actually fit data that will cover the entire data space, okay? So the empty space actually grows exponentially with the increase in adding new features, okay? And it becomes very difficult for a model to learn the distribution because the distribution itself is quite sparse, okay? So this is what we call curse of dimensionality, okay? So increasing features actually give the challenge of your data to fit the entirety of the vector space, and it turns out that the data is actually very sparse in a big space, so learning any kind of model becomes difficult, okay? So this is what we call curse of dimensionality problem.